So here's another example. I'm going to take the derivative with respect to x of the integral from 0 to x of 1 over 1 plus t squared. So I'm taking the derivative of a function defined with an integral. My variable that I'm taking the derivative with respect to matches the upper limit. And my lower limit is 0, so my lower limit is a constant. I can apply the fundamental theorem of calculus. I know the derivative is going to undo the integral and give me back my integrand, but with the variable changed to whatever that variable is. So 1 over 1 plus x squared. Here's a new problem. This time I'm taking the derivative of an integral. My lower limit is a constant, but my upper limit is not an exact match for the variable that I'm taking the derivative with respect to. I do not have an exact match here. So watch what happens. We actually pretty much use the fundamental theorem of calculus, but we're going to need to use the chain rule. So the derivative will still undo the integral, but this integrand, instead of the t, I'm going to replace all the t's with x squareds. So cosine of t turns into the cosine of x squared. That's the upper limit replacing the dummy variable. I'm going to multiply by the derivative of that upper limit. Well, the derivative of x squared is 2x. This is a great answer, or you can see here, rearranged it. You could write 2x cosine of x squared or cosine of x squared times 2x. Equivalent. Try this example. I'm taking the derivative of an integral, and things are kind of right, except my upper limit is the constant and my lower limit is the exact match for the variable that I'm taking the derivative with respect to. So notice I can use the order of integration property to change the order of integration. So instead of the derivative of the integral from x to 5 of 3t sine t, I'm going to have the opposite of the derivative of the integral from 5 to x of 3t sine t. Now I'm going to simplify this part. The derivative of this integral, well, now all my three properties, all my three requirements line up. I'm taking the derivative of the integral. This x matches this x. My lower limit is a constant. So this derivative of that integral is going to give 3x sine x, and this negative is just going to change the sign of my answer. This time, neither limit on my integral is a constant. So I'm going to use that additivity property of integrals to rewrite this one integral as the sum of two integrals. So pick any number you want. You don't even have to know or even suspect that that number is halfway between or even in between the two limits you do have. So just pick 0. I can rewrite this. Notice, remember, additivity says the integral from, I would have said 2x to 0 plus the integral from 0 to x squared is the same as the integral from 2x to x squared. So now I can, instead of taking the derivative of the original integral, I'm going to take the derivative of the sum of these two integrals. Notice the integral that I've written first is pretty good. It has a lower limit that's a constant. It has an upper limit that's not a perfect match, but I'm going to be able to use the chain rule. My second integral is a little bit of a problem because it's got the variable in the lower limit and the constant is the upper limit. So I'm going to use the order of integration property to change that around. So instead of adding, I'm going to add the opposite so that I can change the limits. So adding the opposite, subtracting. Now this, I can take the derivative of this sum of integrals, the derivative with respect to x of the integral from 0 to x squared of 2 plus e to the 1 over 2 plus e to the t is going to be this integrand, but with the t replaced by the upper limit, which is x squared. And since that upper limit was not just an exact x, I'm going to have to multiply instead it was a function of x, I'm going to have to multiply by the derivative of that upper limit. So that's where this 2x comes from. Here's the subtraction sign. And 1 over 2 plus e to the t. All the t's are going to get replaced with 2x. So there's going to be 1 over 2 plus e to the 2x, but that's not just an exact x. It's a function of x. I need to multiply by the derivative. That gets full credit. But if you want to simplify it, maybe it's a multiple choice question. You might have to rearrange it so it looks like one of your answer choices. Final answer. All right, so the second part of the fundamental theorem of calculus is the one that we already saw at the end of 5.3, which is you can use an antiderivative to evaluate an integral. So if f is some continuous, little f is some continuous function, and capital F is any antiderivative, remember most functions have an infinite number of antiderivatives, then the integral from little a to little b of little f is capital F of b minus capital F of a. There's a place for that on your important facts paper if you didn't already fill it in, and we'll do some examples from your handout.